Welcome to another lecture in Advanced Mathematics. Today, we will review our knowledge about matrices and vectors. I know that you have already encountered and studied matrices and vectors in your previous mathematics course. But for this course, we will take a short tour on this topic, as this is a refresher, because this is essential in the study of numerical techniques. In this course, you will encounter more operations and matrices as you go along. Okay. Matrix is defined as a rectangular array of numbers since not only the values of a number is important, but also its position in the array. The size is often described by the number of its rows and columns. Thus, for the figure below, the matrix is said to be of size n by m, as it has n number of rows and m number of columns. The matrix notation may involve enclosing a variable with brackets, such as this, or with a small letter along with the subscripts I and j, where I is an integer from 1 to n, and j is also an integer from 1 to n. However, a matrix can also be noted using a capital letter, such as with A or any other letters. And also, in denoting the elements of a matrix, the elements are contained inside a large bracket, where the elements in its particular position in the matrix is enclosed. Matrices can be added or subtracted. Two matrices of the same size may be added or subtracted. Let us consider matrices A and B, where they are defined by this following notation. The sum of A and B is therefore C if we let C as another matrix. C is the matrix whose elements are the sum of the corresponding elements of A and B, and they are defined by the following notation, where C enclosed by brackets sub I and j are whose elements are the sum of the corresponding elements of A and B. Similarly, we get the difference of two equal-sized matrices by subtracting the corresponding elements, the same as we did with the sum of the matrices C. Thus, if we let D as another matrix, then D is the difference matrix of A and B, and this matrix is denoted with D sub I and j is closed by two brackets. Let us proceed with following example. Here we are given the matrices A and B, where the both matrices are of sizes 2 by 3. Okay, so you can see here the two matrices of different elements, a different matrix, but they have the same size 2 by 3. Thus, the two can be added or subtracted. Let me see as the sum of A and B, then we will just simply add the corresponding elements of A and B to get the sum like this. So for example, for the first element in row 1, column 1, we can that the elements 4 and 1 are the corresponding elements of A and B, and so on with the other elements. Thus, we get the elements of matrix pad or the product matrix C, such as this. Meanwhile, by letting B as the difference, then we get differences of A and B as D, where the elements of B is subtracted from its corresponding elements in A. Therefore, we have the matrix D, or difference matrix, with the following elements. Okay, we obtained these elements such as 2, 3, 2, negative 9 by subtracting the elements of B from its corresponding elements in the matrix A. Now, in multiplying matrices, the operation is not quite the same with addition and subtraction. Here, considering matrix A of size n by m and matrix B with size m by r, we see that the product C is defined by the following procedure. With the matrix of the product C is the summation of the product of the row elements in A and column elements in B from K is equal to 1 to m. Okay, so this is the general procedure in getting the product when we are multiplying the two matrices. And below is the general notation in getting the elements of the product matrix. Let us consider the following example. Here we have matrices A and B of different sizes and of course different elements. Here the two matrices are not of the same sizes, such as A is 2 by 3 and B is 3 by 2. Okay. Now the multiplication of these two matrices is as follows. The first row of A is multiplied with the first column of B. Okay, so we get there the elements of the first row of A, such the elements 1, 2, and 3, are multiplied with the elements of the first column of B, such as the first element of the product matrix is the summation of the sum of the corresponding elements, such as 1 times 7 plus 2 times 9 plus 3 times 11. Here we get 58. Okay. For the next step, we will consider the second row of A and this multiplied with the first still with the first column of B. So same procedure goes with what we just used with the first element when we obtain 58. Here we get 139. Same goes with the first row of A multiplied with the second column of B. We get 64 and so on. And lastly is you get 194. Therefore, the product of A and B, product of B is C with the elements 58, 64, 139, and 54. Okay. How about if a matrix is multiplied by a pure number? This is what we call as the multiplication by a scalar. Okay. Suppose that we are to multiply a matrix with a pure number or a scalar k. So what is this pure number? It could be in a number, a pure number, in integer that we seek to multiply into a matrix, to a matrix. Then we get a product matrix C as a product of scalar k and matrix A, and this is represented by this following equation. Therefore, the elements of C are the products of the scalar and the elements of A. For example, we're to multiply matrix A with these elements by scalar 5, k equals to 5. The product is therefore obtained by multiplying each element with 5, such as this. We multiplied each of the element of A with the scalar 5. So we multiplied such as we multiplied 5 before, 5, 0, 5 and 1, and 5 and negative 9. And here we obtain the product matrix C with these following elements. Alright. Now let's consider a few more examples. And here we are given with matrices A, B, X, and Y. Each of these matrices has different elements, different sizes, and even one matrix involves variables. Let's go with the product of A and B. Okay, A is multiplied by B. Okay, then given A and B and this their elements and sizes. Same procedure with the previous example. We get the you get the product or the elements of the product matrix by using this operation, and here we get the product of A and B with elements 16, 14, negative 13, and 10. And here we get the size of the product of A and B of size 2 by 2. Okay, so take note that out of multiplying the product, the matrix A with size 2 by 3, and is uh, multiplied with B of size 3 by 2, you obtain the product matrix of size 2 by 2. Okay. Same goes with another element, and the last element, and we obtained the product of A and B. Now let's reverse the order. Let's reverse the order such as that B is multiplied by A. All right. So we'll take a look if there would be difference if we reverse the order of the two matrices, such as we multiplied firstly B with the size of 3 by 2 to with A with the size of 2 by 3. Seeing the same operations as we did with the previous example for multiplication, we get a product matrix of size 3 by 3. Okay, so what happened here? Okay, so using the same operation, when we reverse the order of the multiplication of A and B, B and A to B and A, we obtain a different size of matrix. Now we get this product matrix of elements 20, 30, 11, and so on. And this will be explained shortly. Okay. Now let us consider getting the product of A and the column matrix X. Okay. So column matrix A is multiplied with the column matrix. Why it is called a column matrix? This is because X is a matrix composed of only of elements with only one column. All right. So what happened when we multiplied the a 2 by 3 matrix with a column matrix? Okay. So here, the same procedure with the previous example. Here we get an element, column. Here we get the product matrix, which is a column matrix of with elements 2 and negative 5. Another column matrix Y, which involves elements that are variables. Okay. So the same procedure with we used with the another column matrix X. We obtain this this product, which is 3 y1 plus 7 y sub 2 plus y sub 3, and the second row is negative 2y1 plus 2y sub 2 minus 3y3. Okay, so this is just the same with when we multiplied A with X. Only the column matrix X involves coefficients or numbers. Okay. Finally, we will multiply A with A scalar 2. The product as this matrix with all the elements multiplied by 2. Alright, so we just simply multiplied all the elements in A with 2. Alright. The size of the matrix of the product of matrices with size MIN, M by N, and N by R is equal to the size of the number of the column of the first matrix and the row of the second matrix. Okay, hence this relationship. Alright. That is why when we reverse the order to get the product of A and B, we obtain different matrices with different sizes, such as that when we multiplied a 2 by 3 matrix, 2 by 3 matrix, the A multiplied with the 3 by 2 matrix, we obtained a matrix, the matrix of product with the size 2 by 2. Okay, so this relationship was observed when we multiplied in the previous example. In the previous example, the A multiplied by B. Now let's take a look at another relationship. Uh, when we multiplied matrix B of size 3 by 2 by A with size 2 by 3, we obtained a larger matrix, a larger product matrix with size 3 by 3. Okay, so if you have remembered, this relationship was observed with when we reverse the order of the multiplication of from A to B to B and A. Right. The general relation is therefore denoted by the following, where B is a column matrix with rows from 1 to I, and by that definition, we can write the following sets of equation. Okay, from this general relationship, we can write these sets of equations. Okay, remember that the elements in B are the corresponding products when we multiply the elements of A with the column matrix X. Okay, so we're given with a matrix A multiplied with a column matrix X, and we get the product B, matrix B with elements B1, B1, B2 to B sub n. Right. So to simplify this, uh, this relationship or this set of equations can be represented by simply by this equation AX equals B. Okay, how where A is any matrix and X uh, is a column matrix and B is a product matrix of the two matrices. Okay, and this is represented by this. Okay, we will further simplify this by instead of such as we already know the X is column matrix of variables X, we just simply represent it with a single variable X. Okay, such as this. With this example, when we have this matrix A of these following elements multiplied with X, simply representing a column matrix from X sub 1 to X sub n. Okay, where the X sub n corresponds to the number of rows of the matrix A. Okay, so here when you do a multiplication of this matrix, we obtain these following sets of equations. Okay, with your pen and paper or notes, please just do here a simple checking, or do a simple verification with your pen and paper. Okay, remember that this X represents a column matrix X with elements X sub 1, 2, and for this example is X sub 3 because there are 3 rows in the column A. Okay, so this is the following sets of equations uh, from this multiplication of matrices. Okay, let's take note that two vectors each with the same number of components may be added or subtracted, and two vectors are equal if each component of one equals the corresponding component of the other. Okay, let's take a look uh, at the special cases of multiplication of two vectors. Okay, so first case is when we multiplied a, a row and column vector. Okay, so the first vector is a row vector. So it's because the elements is elements or is only a row, while it is multiplied with a column vector for 1 to 3. So we are multiplying a row and column vector. Now, in doing so, in doing the multiplication, we get the product -5, a single element vector. Okay, what happened when we reverse the order? So when we reverse the order, we multiplied a column vector with a row vector. What happened? A we obtained a 3 by 3 uh, product vector. Okay, so when you see we see here that it still follows. It follows the relationship between the sizes of the two matrices that are to be multiplied. Okay, what happened for this first case, since it has the first matrix, the first vector to be multiplied is size of 1 by 3, and the second is size of 3 by 1. We obtained a 1 by 1. Okay, so the size of the product is equal to the number of number of column of the first and number of rows of the second. I mean, I'm sorry, the number of rows of the first and the number of columns of the second. Right. Same with here. We have 3 rows and 3 columns of the two matrices. Thus, we get a 3 by 3 product. For further readings on this topic, please read the topic on the book Numerical Analysis by Gerald and Whitley, and the Numerical Methods for Engineers by Chapra and Canale. Okay, I've already shared to you the links of the ebooks of these books, ebook versions. I've sent you in the through the in the VCE and Google Drive link. So you can see there a few more examples, and further readings in this topic. Although we had what we have discussed right now is also already covered the whole review of matrix and vectors. But the preceding lessons, preceding lectures, will be discussing more on special types of matrices, vectors, determinants, and the Cramer's rule. That is all for now. Thank you and see you to the next lecture and consultation. Thank you very much.